Yeah, Janice. I think we're set. Stand by, everybody. We'll get the webcast underway.
Good evening. On behalf of KPCC and Southern California Public Radio, welcome to the Crawford Family Forum. For tonight's program, The Brave New World of 3D Bioprinting. And now, your host for this evening, co-producer of SCPR's science series, Next, People, Science, Tomorrow, Matt Kaplan.
Thank you so much. Welcome to another evening devoted to the abundant future that may be coming within our reach. Replacement parts for humans, that's nothing new. I bet somebody here tonight has a false tooth or two. You know, the first of those may have been implanted or used back in ancient Egypt. How about a hip made of, I don't expect you to raise your hand, a hip made of titanium or ceramic material? An insulin pump that maybe has taken over for a worn-out pancreas? But nobody here would say that these devices, these macro devices and constructs, that they're alive. They aren't made of living cells. And I don't think anybody would argue that they work better than the living organs and structures that they've replaced. Not yet, anyway. Consider the kidney machine. You know, undeniably, that's a real life-saving technological miracle. But it really pales by comparison to the little half-pound, or for many of us, the 2 half-pounds of living tissue that do that amazing work, that really come as original equipment in our bodies. Billions of years of evolution turns out to be maybe a slow, but a pretty effective way of designing for life. So why not emulate nature more directly? Why stainless steel and plastic when there's a much better example to follow? Well, because it's damned hard, that's why. But the first sort of tentative steps are being taken, and some of those steps are even proving, I think we're going to hear tonight, to be profitable. They point to a medical future that even Star Trek's Leonard McCoy and Beverly Crusher, I think, would marvel at. We are really wonderfully fortunate to be joined by 3 guests who are at the forefront of this work this evening. Andrew Hessel will be up first. He's a futurist, or really what he calls himself is a genomic futurist. His website welcomes us to the world of synthetic biology, and we'll ask him about that term. Talk about your brave new worlds. Andrew is a distinguished researcher with Autodesk, the company best known for computer-aided design or CAD software, and for 3D animation tools like 3D Studio Max and Maya that have created entire living universes on movie and video game screens. We'll ask him why why companies are now getting into this and why that company in particular has decided that it's time to move into biology. Andrew has been co-chair of bioinformatics and biotechnology at Singularity University. That's that forward-thinking institution that was founded by Ray Kurzweil and Peter Diamandis up north here in California. He's a fellow at the University of Ottawa's Institute for Science, Society, and Policy and has given scores of talks to groups ranging from the FBI to the UN. He joins us here on stage via Skype. Please help me welcome Andrew Hessel. So Andrew, you're at home in New York this evening?
I am tonight, Matt. Yes.
Great.
Hi.
So what is this thing that's right on your homepage, synthetic biology, which I think is behind much of what we'll be talking about this evening?
Synthetic biology is a really fascinating field that's been growing quite quickly for the last 10 years. It's really an extension of the genetic engineering technologies that we've been using for about 40 years, but kind of moved into a digital realm where the design of the genetic constructs can be done pretty much all on computer and then attached to a type of machine we call a synthesizer that can actually print the DNA. It's really like a little 3D printer for the DNA molecule. So it's taking genetic engineering into a digital age and really making it easier and more accessible for people to start learning about how to program cells and living structures.
So this really goes beyond just the sort of printing of tissues that we may be talking about this evening. In fact, it goes beyond printing, right? I mean, there are a number of techniques that have been at least beginning to prove successful.
Well, the way I look at it is, we're talking tonight about bioprinting, which is really using cells as a type of ink, but synthetic biology actually allows us to go under the hood of cells and really start to adjust and program cellular metabolism from a very basic, fundamental principles up. So really anything under the hood is accessible. So it allows us to really start to consider how we might manipulate not just one type of cell or one type of organism, but pretty much every type of cell and every type of organism using a common programming language.
So not just grow new tissues and new cells and perhaps one day organs, but maybe even improve on them.
Exactly, and mixing and matching from different cellular processes across, the spectrum from nature.
So is it fair to say you think that this field is going to change the face of medicine and really maybe the face of humanity?
I think it has the potential for doing that. Biotechnology in general has had that promise since, the discovery of the DNA molecule and understanding cellular life. What's really getting interesting is now that the tools are becoming more computerized and digital, they're also becoming more accessible and understandable, which is allowing a larger audience of really to come in and explore it from professionals in areas that are non-biological to really just a whole new generation of biologists that aren't looking so much at dissection and taking cells apart or organisms apart, but actually thinking about how they might want to engineer them and program them. It's really quite exciting.
This is another topic which we really ought to devote a whole evening to sometime, open genetic engineering, and really talk about opening a Pandora's box. But I know you're a big fan of it. We'll have to have you back when we have that other discussion. Like any new field that really proposes something as exciting as biofabrication, bioprinting, there does seem to be a lot of hype growing up around this topic we'll be talking about tonight. I mean, do you think it's appropriate?
I think I think the hype cycle is part of any new technology that's emerging, and it's because it's new and it's interesting, and a lot of people are just wanting to know the basics about it. It usually ends up going through a period after the hype of some sort of rationalization of what's really possible and what can be taken to market. But this, what I find fascinating about this technology is that we're really using, cells are really well known. They've been around for 4 billion years. They're pretty robust. And in this case, it's, bioprinting is actually building on the foundation of digital design and 3D printing that has really, I found articles going back to, I found digital fabrication, 3D printer stories in the media that go back to 1980. So this isn't a new technology. It's already been through several rounds of hype and development. So I think it's not over for sure. But we're seeing wave after wave of evolution now, and it's pretty robust technology today.
And I guess it's safe to say the advances are coming much more quickly now than they would have in the 80s.
Absolutely, and there's a lot more digital architecture for people to build on. A number of groups that I'm watching these days are starting to build 3D printers from scratch. So there's just a lot of real access to fabrication, to electronics, to software, to computing in general. So we're seeing a convergence of different technologies that should propel this wave of development for a while. There'll always be some hype. But I think the things that we can actually accomplish with it are getting really interesting now, and we'll start to see some of these move to market quickly.
We've got to get that curve of new technology that is shown all the time. We could use that in just about every one of these next programs, where you see that sudden increase in interest, and then people become a little disillusioned and the interest falls off, but then you see it slope slowly back up as that technology really reaches its potential. We talked about Autodesk, and you're affiliated with that company. Why is this company that is pretty successful with much more traditional forms of design, why do they see this as an area that they need to get into?
I think it's because we really look at living systems and nanotechnology as a whole new domain of design that really wasn't accessible before with digital tools. Autodesk makes software tools for designing, visualizing, simulating complex systems. Really in a number of different verticals. Construction is one that it's very well known for. And most consumers kind of know our work through tools that are used to make special effects in movies. But you know, software tools are incredibly powerful for showing complex systems, for being able to manipulate them and simulate them. And what was really interesting was that we really didn't have this professional layer of tools being applied to life science yet. And the idea of these self-assembling systems rather than these systems that humans have to go out and, you know, manufacture or construct in factories. And as biology's become more digital with with human genome sequencing, with electronic medical records, with just in general the digitization of the sciences, we recognized that there was an opportunity to bring some of these really high-power professional design tools into the space and use that as another vehicle for connecting people together and getting them to really start to explore the design space in new ways. So I was fascinated by the company was interested in doing this. I'd met them through Singularity University, and when they created a bio-nano group specializing in this area, I was just thrilled to be a part of it.
I'm going to throw one more question at you that I will also give to our other distinguished guests on the panel this evening, and that is with the talk of, and even in some places pictures on the web, of rather fanciful, somewhat science fictionist 3D printers printing out a new human heart. How far away from that kind of complex, functioning, dynamic structure do you think we might be? You're someone who's examined this industry.
Well, you know, I'm a futurist, so I generally live in the future. I can tell you that what we have at present, you know, your guests tonight will probably be, you know, are the experts on that. What I know, though, is that these technologies, whether it's the software design tools or the printer themselves, are part of an exponential technology group. In other words, technologies that are changing really, really quickly. And there's another curve for those technologies as well, because they generally look like a hockey stick as they go through their evolution. So wherever we are today, I think it's important to realize that we're probably going to double in our capabilities in a very short period of time, just like Moore's law in computing, and then double again in another short period of time, and again after that. So even if it looks like it's fairly crude today, depending on the doubling times, we could be in a very advanced situation within 5 to 10 years. So I'm not, you know, really probably the most difficult technology to wrangle at this point. It's not the 3D printer. We're getting really good at those. It's certainly not the software. We know that, you know, software is pretty much blankets the world today, and it can be very complex. It's really understanding how to manipulate cells and cell technologies. And you know, even outside of the body, so to speak. We've only had the genome for 13 years. We've only had stem cell technologies really on an exponential since really for the last decade. So that's probably the limiting factor at this point when it comes to being able to put cells together, to do complex designs with them, and to really understand how the cells are operating when they've been kind of put together in these artificial ways, development ex vivo, so to speak.
I love that concept of Moore's law coming to bioengineering. Maybe we'll call it Hessel's law. We'll see if
Actually,
that. We'll see if we.
Carlson curve, yeah, but named after biologist Rob Carlson, who first described the exponential curves in life science.
I want to get one of our other guests up here, and I can tell you that as I did my research for this evening, there was one company that showed up in pretty much every article and every web page that had anything to say about this topic. Organovo is barely 6 years old. It's run by our next guest. Keith Murphy left Amgen after 10 very accomplished years to become chairman and CEO at Organovo. He also serves as vice chairman of the Alliance for Regenerative Medicine. And if you want to go into logo design heaven, just go to that alliance's website and you will see this amazing collection of little nicely designed logos. Speaking of design issues, it's amazing to see that there are more than 120 organizations and companies that have already joined Organovo in this alliance. Organovo is based not far from UC San Diego, but Keith Murphy is here with us this evening. Please help me welcome Keith Murphy. Have a seat.
Thanks, Matt.
So last July, you got to ring the bell at the New York Stock Exchange. Pretty cool. How's business?
It's going very well, thank you. And we're working very hard at translating the 3D bioprinting into solutions, and so far so good.
And it is now a publicly traded company.
Yes, since February 2012, we've been publicly traded, and we uplisted from the OTC to the New York Stock Exchange MKT in July.
Congratulations.
Thank you.
The Organovo homepage says, imagine the questions you can answer in 3D. What does that mean from the Organovo viewpoint?
Well, specifically, that's in terms of our outreach, in terms of the partners that we look to work with. So pharma companies, academic researchers who have a need for this kind of tool to answer questions in their basic research. And so for us, that means that the reliance on what I'll call 2D tools, which is cells in a petri dish, for in lay terms, sometimes leads us to wrong answers. Leads us to build systems that don't give us the best picture of what's going on in the body. So we're asking people to think about how they use cells today and how 3D can help them understand better how the biology of the human system works.
So we should make it clear that right now, Organovo, it's not like you're building those livers that we sometimes see in the press, but you are building tissues that are being used by other companies for more accurate testing of substances on human living cells.
Yeah, that's right. I think that if you look at the history of tissue engineering, we started maybe 20 plus years ago with the goal of building an organ as a whole, and we started by taking polymer structures and shaping those like an organ and then putting cells on top of that. So that's one way to approach the problem. What we're doing at Organovo with 3D bioprinting is approaching that problem from a slightly different angle. So we're not making large liver structures, but we are making very, very tiny liver structures that actually work like the liver. And so the problem with the largest structures is they haven't really translated into any performance that can be compared to what's going on in a human. So our livers really are performing very much like a human liver. They just happen to be very, very small. So the next steps, if you're trying to move towards the goal of making full organs, is building upon that and making those larger and larger.
You've brought a video along. Would this be a good time to take a look at that?
Yeah, I would preface it by saying that this is kind of the video for how we would use the current models that we have. So the very small tissues that we make can be used in what's called a multi-well plate in pharma research, and I can walk through it as we go if you want to.
Great, okay. We can roll that now.
So the bioprinter will actually start. Can we mute tissues with its we'll actually start by actually building inside each of these wells. That's a 96 well plate, which is very commonly used in life science research. You can do many experiments at once. You build the same tissue in each one. And you're going to actually build a little tissue in there. It's going to actually mature, so this is part of the self-assembly of what's going on there. So you'll see capillaries form inside that. You see a little microstructure grow because these are living cells. Then you can hit it with something that causes disease, a disease-causing agent. And then in each of the different wells, you can put a different chemical compound or perhaps a different concentration and try and heal that tissue. So we're building these little samples of tissue that can be used to study to find new drugs. And it's going to be superior to that 2D cell culture, largely because you're making a tissue that's got a thickness to it. And that mainly means that the cells are interacting together in the way that they do in the body more than they're interacting with the plastic. And so you see here this graphic is showing you're essentially saying, I can get more hits because I've got this living tissue that I'm working with. And it really does, in our hands, seem to be living tissue. So we actually just announced this morning that the 3D liver tissue that we make now has performed for 40 days, showing evidence of liver function, full evidence of liver function out to 40 days. So Andrew mentioned, we're dealing with life here, and one of the definitions of life is, of course, self-replication. So I can tell you that it's not all the same cells in that 40-day period that started at time 0. Those cells are multiplying, they're dividing, some of the cells are dying off over time, and they're being replaced. So that is a living tissue.
Amazing, really. What people didn't hear there in the narration on the video is at the very end, when they may have seen that liver show up, that complete liver, is that you do speculate in the video about the time when we can take that very limited sample of living liver tissue and create an entire organ or maybe a section of one. Is that the ultimate goal at Organovo?
Well, we have nearer term goals than that in terms of building tissues, but that's one of the potential uses of the platform, the bioprinting platform that we're building. And we work towards that longer term goal by partnering with a number of academic centers across the board. So there are these bioprinters are in placement at academic centers using federal research dollars to try and advance this field and get us towards those goals. In the nearer term, we do have a corporate goal of building tissues that are going to be useful in a surgical setting. So replacement tissues used in a surgery to impact a patient's health, but those are going to be simpler tissues. So there are a lot of limitations that one has to consider. The primary one being that, and this is across the board in tissue engineering, no one has ever achieved tissues that are very thick to date because no one can yet build blood vessels inside of tissues. That's a key hurdle that the whole field has to get across before we can start to build very thick tissues. Every cell in one of these living tissues needs oxygen and it needs nutrients. And the only way those are delivered is through a vascular system in our body. And in these cells, we rely on diffusion, which limits us to 1 millimeter or less of thickness. In these tissues, we rely on diffusion. So today we can make things that are 1 millimeter thick or less, and we contemplate ways we can get tissues to patients that are going to be that size or smaller. So you think about things like heart muscle patches to repair function. You think about blood vessels, which have a wall thickness that is smaller than that. And you think about things like nerve grafts that can repair nerve gaps in the body. These are the kind of things you'll be seeing on the shorter term time frame going into clinical trials.
So even though we saw tiny capillaries forming just as they would in human tissue in the body, that's not to say that we're at the level of actually having a vascular system.
That about doubles, and those are microvascular networks. I called them capillaries when I said that, because they're not yet perfused like capillaries, right? So there's not a central pump pumping through those. It's,
no heart.
It's passive diffusion. So they're microvascular networks. That's what gets us to 1 millimeter thickness. Without that, you'd be limited to 500 microns or smaller, half of that. So that's one step in the right direction. On the other side of the scale, we're bioprinting branched tubes. So we do print human artery structures at Organovo. We started with linear conduits, so long pieces of artery that's a 3-layer tissue made of the 3 cell types that are in a human artery, and those cells are taken from individual people. And now we've moved to branched, if you will, into literally making branched tissues that are similar to that. So you're making that macrovascular structure, and now we've got a bridge between those two. How do we get that to be perfused and go down into and flood those capillaries? So it's a long process, and it's not our main focus, but it is something that we're working on.
Tell us about the printer, the bioprinter that Organovo has developed.
It's a labor of love for us. It's been a long time in coming to get to this. I think one thing you have to remember about the bioprinter is that, and I think Andrew described this well, is that it's not necessarily that the bioprinter does anything magically from a mechanical engineering or electrical engineering perspective, but it gets the cells in position, and that's where the challenges really are, is in the behavior of the cells at that point and after that point. But it took so many different disciplines to come together and even get to that point to build a bioprinter that would accomplish that I think even achieving that has been a real feat. So the professor that developed this technology, Gabor Forgacs, he's a biophysicist. He was working with folks who were skilled in mechanical engineering and electrical engineering to get the tissue, to get the cellular inks to behave the way they did, and a lot of folks from the biological sciences coming together to make it happen. And so the printer is essentially it's about the size of this table in terms of its footprint. It fits inside a biosafety cabinet, which is how we keep all the tissues completely sterile. And it can print with plus or minus 20 micron precision, and it can build things that are actually quite large in the sense that we can achieve placement in a large envelope, but the limitations of thickness really come in.
Using inkjet technology, not that different from what I have next to my computer at home?
So inkjet is one of the technologies we use at Organovo. The core technology that came out of the Forgacs labs, the professor I mentioned earlier, who's one of the founders of the company, was actually slightly different than inkjet. So inkjet can print a layer of cells, or it can print cells in a pattern on a layer, and it's a little more difficult to build up a thickness of cells. So Dr. Forgacs' technology technology actually built things that were on the order of 20 cell layers thick very quickly. So each layer is more like 10 to 20 cell layers, so you can make thicker tissues faster. And then we use inkjet as a complementary way to build things like epithelial layers, which are thin layers.
I see. Okay. And already in this very young industry, there's a growing diversity in the techniques that are being used to build up these tissues.
That's absolutely the case, yeah. And there's a number of different technologies. We tend to think about bioprinting as mainly focused on building with the cells, but some people define it even as, if you think about it, what I was describing about making polymer structures that you could put cells on top of.
Sort of a lattice work.
A lattice work. Someone else in the field might say, oh, I bioprinted this lattice work, and that's made of a bio-friendly material, and then the cells go on afterwards. So there's different ways you can define things.
With that in mind, let's bring up the last of our guests. Now, only a couple of miles separate Organovo from UCSD, the lab there that is run by our next guest. Xiaochen Chen is a professor in the Department of Nano Engineering at UCSD. He's go Tritons, I have to say that for my daughters. He's also on the faculty of the university's Institute of Engineering and Medicine. He came to California from an endowed chair at the University of Texas, Austin. Dr. Chen also served as program director for the Nano Manufacturing Program at the National Science Foundation. He's received many honors and awards, and is an associate editor of the Journal of Biomedical Nanotechnology. Please give anything but a nano-sized welcome to Dr. Xiaochen Chen. Welcome, Dr. Chen.
Thank you very much.
Now, we already heard Keith talking about different techniques being used within Organovo, but also across this growing, I guess it's not fair to call it an industry yet, but across this growing field. Your lab, you explore some of these, don't you?
Yes. So I'm an academic researcher. So we have hypothesis-driven research. So we look at cell is on the order of 10 micron or 5 micron. So if you want to really print authentic tissue in the future, your resolution has to be down to micron or even nano scale. At this moment, from all these commercial printers are on the order of, I would say, 100 micron or 200 microns. And so what we are pushing now is to get the printing resolution down to a single cell or even smaller level. So if you see these slides, we call 3D bioprinting at micro and nano scale.
Yeah, let's go to your slides right now. We've got the first one up there, just that title slide, and we'll go on to the next one.
Yeah, so this slide actually tells you the basic idea. It's different from what Keith described. He used nozzle or those physical confinement to deliver the gel or cells to the...
This looks more like the kind of 3D printer that I've seen for years, where you have that liquid that is being hardened.
Yes, exactly. So we actually use a photon or laser beam to shine on this polymer, this called photolith sensitive solution. It's a magic solution. So when you shine the light, this spot becomes solid from liquid. So when you're dealing with light, you can scan, like you play with a laser pointer from X, Y, Z. So that can all being controlled by a computer, digitalized softwares. So eventually you can build a very complicated three-dimensional structure, point by point and layer by layer. So on the right side, I have this picture showing that this is a single cell about 10 micron sitting on this nanoscale web, and I'll come pay some attention to this special geometry of the web. I'll show you later. This is not a regular web. It's quite a unique web.
So we'll go on to the next slide.
So so previous when we do use a laser printing, the idea is to manipulate those photons so you can get very fine structures But usually the process is slow when you do point by point and then layer by layer. Although you can build a large structure, but it's too slow. A lot of time the cell inside liquid will not be able to survive. So we look at this PowerPoint presentation. When you do that with a computer projector, this image show up on the screen simultaneously with all these patterns, letters, pictures. So we borrow exactly the same idea. Can we project this pattern directly to the polymer solution we just saw? So and that allows you to do very fast printing. There's a website talking about lightning speed printing. So I will show you later, we can print complicated structures within a second or 2 seconds.
Now, before you leave this slide, I think there it says, I can't see it here, but I did earlier, DMD, which is the digital mirror structure that is another nanostructure, right? That's maybe inside the projector we're using here.
Yeah, for each projector, there's a chip called digital micromirror array. This is done by Texas Instrument in Texas. So it projects in this size of a couple of millimeter size chip. It has millions of micromirrors inside. Yeah. So each mirror will serve as like a laser point. So that's why you can project all these images simultaneously. Without scanning.
Are you using ultraviolet because it's the smaller wavelength that gives you more precision? Or?
You can use visible light as well, but most of the time, those polymer material solution we are using is more sensitive to UV light.
Okay.
Yeah.
All
so
right.
And this actually, is similar to like you playing movies, like old-fashioned movie. You have all those film one by one coming out. This figure actually show exactly the same concept. That's why it's so fast. You don't see actually each layers. You just keep seeing all these images coming out of the screen. So and we change the screen to the polymer, and then you print the structure.
Okay. And the next slide.
So this on the left side, actually, I show you. That we can print, anything that you can design, and
that
if
lattice.
you look carefully on this screen, on the left side is a porous material with square type of pores. On the right side, there's a special geometries. As you can see, if you play it again, the left side when you pull, it shrink in the y direction. On the other side, actually expand, and that kind of material does not exist in the nature, but we invented, and there's a lot of use out there. For instance, if you're doing hard patch, hard can expand and shrink without any shrinkage, without any wrinkles. So if you can use this kind of expansion materials, you can eliminate the wrinkles when you try to put this type of patch with cells to fix damaged hard tissue.
So to clarify, the web that we're looking at there, that's not living tissue, but you build the living tissue, you use that as the lattice or the framework for the cells that are deposited.
We have a couple of approaches. So this is just purely material perspective. Later on, I'll show you another slide that we actually encapsulate cells inside, because when you do this liquid-based printing from liquid to solid, you can put cells inside liquid, then you shine the light will lock everything in the spot. So then you can tell where the cell to go in your 3D structure as long as you can design it.
And you build up layers this way.
Exactly.
Yeah.
So I haven't finished up this slide. On the right side, you can see those are vasculature type of geometries. And then this can be very, very complicated in 3 dimensions, from millimeter big tubes all the way to micron vessels. It's from engineering point of view, this type of structure is very hard to produce. But with our 3D printing technology, as long as we get an image, we just print this continuously in 1 second.
So unlike what we heard from Keith, where that sort of capillary-like structure was being generated by the cells themselves, does that mean that what we're looking at here, that network of that branching design, that was actually designed in as you created this?
Exactly. So original picture, before you print, you need a digital data. The digital data came from vascular structure of the rat. So whatever you have, like see from CT scan, MRI scan, as long as you give me the digital data, I'll print it. So we will basically use those geometric cues to guide the cell later on when you try to put cell inside.
Fascinating. Shall we go on?
Yeah, please. So talking about living printing, live printing, we do encapture the cells inside those gels during the printing process. So we don't just print a pure plastic material. We print living tissues. Okay. So on the left side, you can see those are cardiac cells from neonatal print on the gel. There's no pattern, so you can see they actually can print. Can you play this one?
There we go.
They can beat. So you can see that the beat.
Oh, look at that! You can actually see that with the cardiac rhythm.
Yeah, cardiac cells are interesting. So they beat after a certain time. That's why you can pump blood with those tissue. On the right side, which I would like to show you that there's a big difference when I pattern those gels, again with the cell encaptured. Then you can see that the beating frequency is quite different. So with that kind of engineered pattern, you can control better the cell behavior. Because when if it's a random like a 2D or petri dish type of stuff, the cell don't have synchronized capability or in terms of beating. But when you align them in a certain direction, you kind of put them into an army, so they march on the same frequency.
So we heard Andrew talk about doing this at the genetic level. You're doing it at a more macro, still tiny, but more macro structural level, actually controlling the function of the tissue.
Exactly. Because if you look carefully, from a physiology point of view, the heart tissue actually has multiple layers, and each layer actually you have aligned structure inside. That's why the cell can have those normal beating. Otherwise, if it's like single sheet, then they don't beat well with control.
I think you got one more here at least?
We have one more.
Okay.
From research point of view, we want to understand how cells behave in those kind of gels. So this actually show you just a couple of cells, not like the previous one. We have lots of cells. Here you have only like 2 or 3 cells. You can see they actually can beat. And with this kind of technology, we can measure how the cell interact with each other, individually, and we actually have tools like those fluorescent beads or other force measurement to see how strong the cell beating force are.
So we are demonstrably in the very early stages of, and I'm going to ask you the same thing that I asked Andrew and Keith, of going from this level to someday, can you foresee building a heart?
I think it's possible. There's a literature already been published by a group of people in Massachusetts General Hospital. They don't use those scaffold-based stuff because this still, when the heart tissue are so large, and we have trouble making larger structure. We can do well in micro nano scale. So what they did is to decellularize the heart. So it's basically they get a heart and then wash it with detergent. So you basically wash away all the living cells, and you end up with only the skeleton. That basically is a collagen.
The collagen framework.
Just the
architecture. Was built when the heart was built within the body.
Exactly. Then they put the cell back, and it turned out there's a certain percentage of the functionality of the heart to be recovered. So think about, they did it in their medical way because they don't do bioprinting. And if we can work together with them better, if we can make those collagen-based scaffolds, 3D, exactly like this decellularized structures, then we certainly can make this work in the future.
Andrew, this must be the kind of stuff that gets you so excited about this field.
It really does, because as we start talking about 3D printing any structure, that's exactly the types of technologies that we've been working with and have a lot of experience with, and already is starting to move very mainstream. So being able to create software tools that can learn alongside the researchers working in this space.
Froze there. There, you're back. Sorry, we lost you for a moment there, Andrew. Just repeat that sentence.
Just being able to be able to make software tools that can learn alongside the researchers working in this field and allow them to extrapolate, model, and simulate the types of structures they want to make. So really a collaborative framework for being able to share this type of information. That's really exciting. Plus, much next generation tools for printing it out.
Keith, you also looked like, you were nodding so enthusiastically during so much of what Xiaochen was telling us. This is obviously exciting to you too.
Yeah, I think it's exciting for everyone. It's exciting to think about the future potential. It's exciting to me to see the work people are doing. I was asked recently, what is the most exciting thing about the technology? And for me, it's actually that at Organovo, we've built just this tremendous team. And to watch these researchers go to work with the technology and the platform that we have, that's what makes it come to life, because they've got to independently work with the bioprinter to make things happen on each project. And you see them using their creativity and using the tool to achieve things that haven't been achieved before. That's what's really exciting, is to see it opening up like that over time.
So Xiaochen, has he already started to steal your postdocs?
Yeah, I wish, we do have lots of students going to work for Organovo from our bioengineering department, from our other engineering departments.
To make a life science cluster, you really need a lot of parts, and one of the reasons the company's in San Diego is because of the life science cluster down there, and UCSD is a huge part of that, and we have a large number of employees who have degrees from UCSD.
What about the broader community that is growing up around this? We talked about that alliance earlier, which already has 120 companies and organizations. This is still in the very early stages, but there are obviously a lot of people who are sinking money and research time into this work. Keith?
Well, you're absolutely right, and it takes a lot of different technologies to make this happen. So Andrew was talking about synthetic biology, and I would just say at Organovo, we actually are very focused on being a 3D platform and enabling 3D biology, but that always requires cells. We don't work on cell technologies. We don't work at that level, but there are so many companies that do. There are so many great researchers working on cellular technologies that we can take advantage of those. So an example of that would be that we've printed the 3D liver that I was talking about earlier out of cells that were biopsied or were taken from human cadaver liver, but we've also done it with what are called induced pluripotent stem cells. Those are skin cells that were taken from an individual person, taken backwards so that they're more like an embryonic stem cell, and then turned into liver cells. And then we can use those in the same way. And it's efforts like that, the advancements in all the different technologies, that really are going to make breakthroughs happen.
Andrew, that would seem to sidestep a lot of the ethical objections that some sections of society have had to using stem cells for this work.
Absolutely. Although I don't spend my days working on stem cells, in the early days they were being harvested from fetal tissue, and that created an ethical backlash. Today, that's really historical. Today we can take cells from virtually any part of the body, and as Keith said, turn them back into stem cells and then forward propagate them into virtually any cell in the body.
Xiaochen?
Yeah, I want to add to this, in addition to the ethical issue, that to be eliminated if you use human-induced pluripotent cells. The other important contribution of this type of cell is it's a patient-specific information. Okay, so you get the cell from your own, not from other people. You got it from your skin, and then turn into functional cells like cardiac cells. Then I put this type of cell in my gels in the 3D micro tissue. Then if I test, for instance, like a drug screening purpose, if I use a certain drugs and to test how toxic this drug is to your cardiac cells induced from your skin cell, then it's very patient-specific. A lot of time, one type of drug work with person A doesn't mean it'll work with patient B. And so I think that's another important contribution of this type of cell coupled with the 3D printing technology.
Yeah, some of us have even heard commercials, I think, for individualized cancer treatment based on someone's individual genetics.
Right.
Yeah, that's absolutely right. We're working on that now. So one of our academic partnerships is with the Oregon Health and Sciences University. They're in Portland, and they have a major grant from Phil Knight, the chairman of Nike, and they have access to a lot of cells from patient biopsies, and we have a bioprinter there. We're working very closely with them on developing ways to build cancer models that can be used for individualized therapy and used in drug development as well.
And of course, another advantage of this has got to be that when we reach the stage where we're replacing sections of organs, tissues, the immune system of that person is going to say, yep, that's okay with me, that's a piece of me. I didn't call on anybody, but Xiaochen, right?
Yes, exactly.
Andrew, since the ethical issues of stem cells seem to have been taken care of, that was a concern of the past, what are really the challenges in terms of society to this? It's hard for me to think of any.
Well, in general, and this is just from my own experience, it's only been really since the human genome was published that we've really started to kind of take ownership of these biotechnologies at a more societal level. There's still they've been difficult to access and understand really since inception, but we've seen as they become more digital, a whole new generation willing and wanting to play with some of these technologies, to try their hand at genetic engineering, to understand cell technologies. And just in the last 5 years, we've seen a whole do-it-yourself community kind of rise up spontaneously from in life science, and it's still growing. So I think it's really just a generational shift where we're starting to come and look at living systems now as just one more thing that we can learn, experiment with, engineer, and potentially turn into not just something for when we're sick or for an elite community of physicians, but is really an area where we can grow, play, and develop new industries around it.
Keith, I want to come back to the design angle here. The idea that we can use software tools like Andrew's company, Autodesk, are developing, to not just engineer our buildings and the vehicles that carry us places, but ourselves. That these software tools are becoming more and more capable. Are these tools a big part of what you're doing?
Oh, absolutely, and we're actually partnered with Autodesk in building 3D printing design, 3D bioprinting design tools, and applying them on our printer. And so it really is enabling to have better design tools. From the start, our printing was essentially almost a code-based thing, where we're building line-by-line software code to execute, to have the printer execute. And I can tell you that when you're asking a biologist or a biochemist or a cell biologist to come in and work with all the different limitations of the printer, and then also ask them to build a software code to tell the printer what to do, you're asking for a very specialized person. So it's almost, this word is overused today, but democratization, right? You're allowing more people to get what they want out of a bioprinter faster by allowing the design tools to improve.
Well, that goes right back to what Andrew was talking about, and this whole growing open community of bioengineering and genetic engineering, I would say, right, Andrew?
Definitely. We're seeing a lot of different people come to the table today, bringing their skills, bringing their passions, and really creating an infrastructure layer in life science that just didn't exist as early as a decade ago. Whole online markets for different types of R&D and communities forming spontaneously around it that are really starting to accelerate the ability to do this work faster, cheaper, and much better than in the past.
Xiaochen, are you using off-the-shelf software, or do you guys grow your own software as well as your own tissues?
We use both. Actually, I think from education point of view, is very, very important, because the students love to design different, crazy stuff, and then they use a bioprinter to print it out, and they can see it right? Just not just a picture in the computer. They actually can print out and take home with it. So it's very, very exciting.
Here's this brings a whole new meaning to I don't have my homework because the dog ate it and loved it. He'd like us to make some more. Talk about some of the other examples around the world that are really impressing you in this field. For example, and anybody can jump in and comment on this, all three of you can. There was just a story not long ago about a lab that grew some brain tissue, human brain tissue. Keith?
So in terms of the brain, it's a very interesting one. So I think there are challenges with brain for bioprinting because neurons are actually not very compact, right? They extend over meters, right? In some cases, making the connections in the synapses. So I think that work was very interesting with the developing. It was it was early. I don't know if it was quite embryonic, but it was very early tissue, early brain cells. And so you have an aspect of the developmental biology there that helps, I think, just like working with, with fetal or early young heart cells helps to make heart tissue more easily because those cells are willing and able and ready to develop tissue from the earliest stage. So I think one of the things we think about in terms of bioprinting and getting to brain is patterning. So we can't always necessarily make the final tissue you can't necessarily expect to design the final tissue and have the printer turn that out. You have to think about creating a template. And so this gets into what some people will call 4D, right? Which is the time element. You don't necessarily start with the end as your initial printed structure. You think about what can we create that will lead to what we would like to induce in the end. And so for things like nerve, I mentioned also a nerve graft, and Professor Forgach early on actually did work where he was doing work replacing in animal models nerve gaps. And he did that not by printing nerves at all, but rather by printing a cell template that was amenable to the nerves regrowing from the animal itself.
When you say the gap, you mean a missing neuron or the synapse?
A missing section, which in the human you would use in things like the periphery. If you had an injury to your arm or leg and you had a gap of nerve missing, if you had a tumor that was near the nerve and the surgeon had to remove the nerve with it, you have on the order of 1 centimeter or greater gap, and you can think about replacing that with these kind of tissues.
It's the biological equivalent of splicing in a new wire.
That's right. Exactly.
Wow. Xiao Chen?
I think it's very exciting to talk about new brain tissues because this Obama administration issued this brain initiative. Okay, it's a big deal for the research community. But the big issue now is from imaging or mapping point of view, you cannot see what's going on inside your scalp. So if you can do 3D printing and print a in vitro tissue, then it's much easier to look what they are doing, what all these neurons are doing there in the tissue, because you don't have this confinement of the head. So basically, you have this in vitro tissue allows you to do many things that otherwise hard to do.
And we should mention that this recently announced initiative by the Obama administration is to model the entire human brain, the most complex machine we know of in the universe. That's quite a challenge, isn't it? Andrew, did you want to get in on this?
I think it's going to be one of the grand challenges of this century. I know I studied bacteria, did that still do that for much of my life, and even just understanding the metabolic processes of a single bacterium is a big challenge. So I think it's great that we have these grand challenges, understand the human brain, which really realistically is the most complex computer in the known universe. But it's great because just that type of interest will spark so much R&D and people moving into the field for decades. It's really important.
Again, for any of you, are there other examples like this that you're seeing that are giving you encouragement in this field? Keith?
Well, I think just speaking from a broad perspective, I think I would like to give some color to people about the field because maybe they don't know. So you mentioned the Alliance for Regenerative Medicine, and it's a consortium of companies, academic researchers, investors like VCs, and patient advocacy foundations, and we all work to advance the field, but the field is more advanced than people realize sometimes. So there are a couple companies in the Alliance for Regenerative Medicine that make $150 million in revenue every year using tissue engineered therapies. Now, they were the earliest companies that worked up skin that could be used to cover diabetic ulcers. So that's the main use of those today. But those are those are living cell grafts that are essentially used not so much for burn, but more for these diabetic ulcer replacements. And each of those companies has 9-digit revenue. So that's very powerful. But there are a lot of stem cell based technologies that are moving forward. There are companies, a company named Cytori in San Diego that has developed a way to extract the fat tissue from your body in a way that can harvest the stem cells in that and then use those for therapies. So that's a very powerful technology. And then Dr. Chen mentioned earlier a wonderful technology that's in early development by some of the academic researchers, notably Tony Atala from the Wake Forest Institute for Regenerative Medicine and Doris Taylor of the Texas Heart Institute, which is a decellularization. And I think that's a newish technology that has real potential to powerfully impact getting towards the organ replacement that we're looking for. And so again, just to recap on that, that's essentially the concept of taking an organ that exists probably from an animal source, because we need regular sources for these, and then washing away the living cells and then putting living cells from the host back on it so that you wouldn't have an immune response if you were able to get that to full function and transplant it. Early days, 5% function has been achieved, so that's early, but has promise overall.
Xiaochen, are there other examples you want to bring up?
In terms of the driving force for getting into the field is I would look at it in a different way, because this is a totally new field. Not so many people are doing that. That's why I'm here. Yeah. So I love to do something that is not so crowded. And the other thing is it's also new for me, so I can learn during the process. Especially this type of work is directly related to human health. So I love to help people if my work can help to do that kind of contribution, I would love to do that.
You have any trouble finding funding, grants for this research?
So far, so good.
So far, so good.
Yeah,
good.
So our grants are, our work are funded by National Institute of Health and the National Science Foundation.
I will chime in on the grant subject, and I think everybody's getting access to grants. But I would note that the relative level of funding that's gone into 3D bioprinting today relative to tissue engineering historically is tiny. And so you ask how long. Actually, I think the question is how much money do we need to put into this to make it happen? Organovo needed to seek financing. Similarly, I think everybody here in the room, everybody in the radio audience needs to make sure to be conscious of supporting NIH-based research, and specifically, we need to have more funding come this way to achieve the ends that we're talking about, because I think that's really what happens in the end. If you think about it as a moonshot, it really, I think the equivalent in today's dollars of the Apollo program was $150 billion. So it took 8 years when you had that much money.
Andrew, I want to get your examples as well, but before we do that, Keith, do you see growing interest from venture capital sources?
Yeah, I think 2013 has been a banner year for life sciences in general, and regenerative medicine within that has done very well. So yeah, I think there's growing interest. People are seeing the benefits of how things are moving forward. There's been a much more receptive investor community. So I do see it growing, yeah.
Andrew, it's your turn. Where are the examples that also make you even more excited?
There's a couple of things that I've been tracking that I think are just really fun, and one of them is a company called Modern Meadow, which is also based on some of these self-printing technologies, except now as they've gotten a little less expensive, you can explore non-medical uses for them. So the company is exploring the use, the cell technologies for the creation of leathers, and also synthetic meats, both very large markets today, and that really are much more consumer-facing than Organovo, but built on very similar technologies and tremendously exciting.
This is why I brought the current issue of Popular Science with me. I was already researching, preparing for this show, And lo and behold, in the mail shows up Popular Science. And there up at the top it says, fake meat is the future of our planet. And in here is Organovo is mentioned, but so is this company, Modern Meadow, which I guess was founded by these same folks that you said helped to start Organovo.
Two of the co-founders of Organovo, and Andras Forgach and Professor Gabor Forgach are the founders, and they run Modern Meadow, yes.
So the idea, as you said, Andrew, is they're making leather. This was never part of an animal. So in other words, they're growing skin, big expanses of it, one day, I guess they hope, and tanning it and making coats.
Yeah, and doing it in a process that should be, scalable and be able to, address a lot of the markets for leather today. They'll start with very high-end leathers for smaller samples, but it's pretty exciting, and it's no-kill leather. As Andras pointed out in a recent talk, he said cruelty is optional.
I saw it. This only just now occurred to me, but if they can grow skin, can't they grow skin with hair? I mean, I would think that there'd be a lot of minks and chinchillas that would want to fund that research.
I know a few people that could probably purchase that. New scalps, complete with hair.
Yeah, I'll get in line. The other examples, when we talked about meat, artificial meat, I think it was in Britain that they already have built the first hamburger out of artificial meat. And I think I believe it was described as not horrible. Any reason why that shouldn't be? I mean, what stands in the way of giving cows a reprieve, Keith?
Well, for a technology like that that's consumer-facing, I think the biggest challenge is just cost, right? So I don't know if there was an estimate published of that burger's cost, but I think it was in the hundreds of thousands of dollars a pound.
Yeah.
So that's a challenge, and these are challenges that biotechnology has wrestled with for a while. You think about some of the great therapies for rheumatoid arthritis and things like that have come out over time, and they were very expensive when they were first launched, in the tens of thousands of dollars per patient. Well, that's partially because they're so expensive to produce. The cells that you grow to produce these are, they consume materials that are very expensive. One of the main things that's fed them over time, and this doesn't feed into the animal cruelty-free, but is actually bovine serum, so cow serum from the blood. That's what's been used to feed a lot of these cells. And since over time that moved to things like soy products, soy-based feedstocks, but they're very, very expensive. There's a lot of technology in those, and drug companies have been working for a very long time to make that cheaper, with some results, but it's certainly not that cheap today still.
Andrew, doesn't this seem like the kind of thing that, maybe Wolfgang Puck would want to jump on? There must be people who could afford this kind of stuff as a status symbol. I'm half serious.
I'm actually seeing the early stages of a boutique food biotech industry where people are just starting to hack food, not necessarily right down to the cellular level, but really hack everything about food. We've seen molecular gastronomy get popular. I think as you start to bring in new flavors, tastes, constructs, really start to get under the hood and again look at some of the genetic engineering of this. We've seen people play with yeast cells to make new flavors and new beers that have different components. I just see essentially the intersection of design, of rapid production technologies like 3D printing, of new software tools, and ultimately just the biotechnologies in general converging to really create a much more playful space, both consumer-facing and addressing some of the big challengers for humanity, whether it's energy or
Oh, you froze again there. I don't know if you can hear me or not, Andrew, but we'll see if you come back.
I can.
There you are. You're back.
Yeah, sorry.
I think we got the gist of it. You know what it kind of reminds me of, Xiaoqian, is that when antibiotics were first discovered, everybody wondered, how in the world are we going to grow this at the industrial scale that it will take to make these an effective way to fight disease? Well, industry found a way. Does it seem like there's a parallel? I'm talking for like the development of artificial meat and so on.
I would say so. coming from academic side, so we are always interested in something that's in the future. So
that's true. This would be commercialization, and you want to be out there on the bleeding edge, which in this case may actually be the bleeding edge. Keith, can you see these kinds of things being scaled up at that sort of industrial level?
Yeah, absolutely. I mean, there are parallel analogies. So I look at biotechnology as one of the examples where when it started out, they were working in 2-liter bottles. So biotechnology, I'm defining, in this case, the narrowest definition, which is training microbes to produce human proteins that are therapeutic. So Amgen was a pioneer in that. You know, EPO, which we all hear about in the context of Lance Armstrong, but of course helps very many patients, cancer patients and kidney failure patients, you know, because it produces red blood cells. You know, that was developed in Chinese hamster ovary cells. They actually produce EPO as a protein. And when we started that, we were working in 2-liter, probably smaller, of course, when it started, but you're talking 2-liter bottles. That's what you're growing these cells in. And then, you know, I know at one point Amgen had something like 32,000 2-liter bottles at once in a lot. But of course, over time, you move to large tanks that can actually make these cells all grow at once. So there's industrialization that has to happen in any field. And, you know, I think we'll see that. What's nice about 3D bioprinting is you start with a level of automation already in it. You know, you've got the printer there to actually do the work. You know, then you have to consider, you know, how you automate everything all the way down, including the quality testing, to keep it cost efficient.
So for those of you who are here with us in the Crawford Family Forum tonight as we talk about biofabrication, bioprinting, we're almost at the point where we're going to go out to you to get your questions for our distinguished panel. So please be thinking about that. And remember, just raise your hand and somebody will come over with a microphone. We'll get to that in just a couple of minutes here. But Andrew, just to go back to you for a second, we talk about doing this at an industrial scale. I'm going to let you talk about that sort of open approach to this once again. You see this happening right down at the granular level of the individual, I'll call it a hobbyist?
I see it going across the full spectrum. We're seeing interest in these technologies from large corporations like the semiconductor manufacturers, for example, because they need to utilize some of these technologies of self-assembly, you know, for next generation chips. We're seeing it to meet the needs of energy. We're seeing it to meet the needs, the growing needs of food production. We're seeing it in the medical space. People forget that, you know, we've had pretty much a flat line in the number of transplantations that we've been able to do for the last 10 years while the wait lists continue to grow. So there's so many drivers for this type of technology, really for society, that I think it's just going to see a lot more investment, a lot more innovation coming into it at all levels.
Keith?
I was just going to comment on the wait list problem, because it's growing, as Andrew said, but people don't even realize, I think as well, that there are many patients who could use an organ who aren't even put on the list. If you're quite elderly and you need an organ, you're not eligible for that first organ that comes through. They're not even going to put you on the list. Or if you're extremely sick and could benefit, but someone else might have a better chance of longer-term survival. So there are a large number, and it might even be a doubling of the size of that list of patients who don't even get put on it because they're really never going to be at a priority level where they're going to get an organ. So, you know, it's a dire need out there, and I think Andrew's right. The more resources that we put towards it, the faster we're going to solve it.
Xiaochen, you already said this is the kind of stuff that's driving you and your research.
Yeah, you know, one good example in terms of scale up is actually the skin market. So 3D printing, or, you know, any basic bioprinting can, you know, has been used a lot for printing those skin tissues.
I'm thinking for like a burn victim.
Yeah, exactly.
Huh.
So then again, you know, nice thing about 3D printing is you take the data from the patient and you measure it, you print exactly the same size as the burn spot, and then put it back.
We'll go to those questions from the audience in just a moment, but that did remind me of one recent example, also in the news, got pretty good coverage, and this was the replacement of a section of windpipe in a patient. We were talking about it just before we started the program tonight, right, Keith?
Yeah, that's a very exciting use of 3D printing. So that was printing a actual plastic piece that could be used to open the windpipe. But to the design side of things, I know that patient's windpipe actual structure had been modeled in the computer so that they could then find they basically I'm not bioprinted, I apologize. They 3D printed out of plastic a small cylinder that could be the framework inside the windpipe to keep it open as a splint almost. But in doing that, they modeled the whole structure using medical imaging data and 3D CAD type systems. So very powerful application of the technology.
All right, let's go out to the audience and see what kinds of questions we have from the folks who've joined us in the Crawford Family Forum tonight. I think we're going to start right back here, sir, with you. Introduce yourself.
Hi, my name is Matthew Boda. I'm a filmmaker, and this is absolutely amazing, by the way. I hate to go too far into the future, but I did want to go back to the last next episode that it was about starships, Gregory and James Benford's book. And so my question is probably better geared toward Andrew, but would bioprinting be what would accompany the Type 3 civilizations as we traverse past the interstellar, areas? Because, that book was talking about downloading human consciousness into a digital device and then having, a petri dish, I guess, of human genomes to wait around in cryostasis as we go those long distances and then bioprint them back up and download the consciousness. Is this something that might be...
We build our humans when we get to Alpha Centauri.
When we get the far distances. Is this the beginnings of that?
What did you think the Star Trek transporter was? It's a bioprinter.
I never thought of it that way.
They put it into code, they send it, and then they reproduce it.
This seems to be the beginning of that. It's fantastic, and I wanted to know if maybe that's what you guys, if your brains might have went there too.
We are way out there. So Andrew, all right, you're the futurist.
I'll use an example to answer that question. I was at a meeting this summer in New York City. The convener of the meeting was a fellow by the name of Dmitry Itskov, who essentially believes that by 2045 we'll have the technology to make a completely cyborg body and to upload our minds to it. So, this may not necessarily take 100 years. It might be very, very ambitious, but I do know that robotic technologies in general are getting fairly good. And you don't necessarily have to build every type of cell type to make a complete limb, for example, or a complete body. It might really just reduce down to some organ systems and a lot of muscles. The brain will I'm not going there.
I don't know why not, Andrew. Resistance is futile. So.
Well, Google might beat us.
That's right. Google, you all saw the cover of Time magazine. Google is working on the challenge of death right now. Well, we'll see how that goes. Let's see where else we've got a question out in the audience. Right there. Hi, sir. Introduce yourself.
Hi, my name is Joe, and I'm wondering about the trade-offs between bioprinting and self-assembly, the way that nature generally does it, as far as making artificial limbs and things.
That's a great question. That's with Matthew's question, I was thinking, gee, why would you print out a human when you could do it kind of the old-fashioned way, but maybe in a large beaker? Does that make sense? I mean, obviously, humans are pretty good at building other humans in something called a uterus. Xiao Chen?
I can start with that. From in the past, the biotech used a petri dish to grow cell and grow tissue. So that would not go anywhere in terms of three-dimensional organ. So that's why 3D printing is useful, because you usually use a scaffold pre-designed by computer or by scanning from the human data. So you have this supporting structure there, and then cell either being seeded later or being captured during the printing process. Then you have this growth tissue or partial organ, Without this supporting structure, I don't think the petri dish will give you a three-dimensional functional organ or tissue.
Andrew, you look like you might want to get in on that.
Really, I'm thinking starships right now.
Well, go back and look at the archive on demand of our last Starship discussion. It was pretty fascinating. Keith?
I can comment and just say, I mean, we certainly see self-assembly at the cellular level. We see the cells reacting to the environment and creating structures. You know, the microvascular networks are an aspect of that. You know, certain cell types, when we create arteries, if we do it in the wrong way, we actually recreate a negative thing, which is neointimal hyperplasia, where the cells overgrow to the middle, kind of like blocking off an artery after a surgery that happens in the body. So you can recreate these disease states. So that certainly happens. And I think what you have in bioprinting now is a tool to really do massive experimentation, you know, hypothesis-based testing, as Dr. Chen points out. But before this tool was available, you didn't have the ability to locate cells in space next to one another and then observe their behavior and interact with them in other ways. Now that you have it, you know, all bets are off. There's going to be so much experimentation. We're going to really learn how to leverage these things, and I think part of that can be learning how to leverage some of the aspects of developmental biology that direct certain structures to form in the body in the early stages.
Is it fair to say, something else that's only just occurred to me, that cells that are derived from cells that are parts of human tissue, that those individual cells want to be part of a structure that is bigger than themselves, that they want to be part of a larger tissue, and they're going to develop the elements that they need, like those capillary-like structures, Keith?
I don't want to get Kantian on you here, but no, I mean, what they want, I don't know exactly. But what I can tell you is that our philosophy is let's give them what we assume they want, right? So if you can recreate outside the body the exact surroundings they have in the body, why would they do anything else other than behave exactly as they do in the body? And we think we're overthrowing some of the old dogma of cellular biology, which was, let's get them into the dish, and if they don't grow in the dish, well, they're just stupid and they're a pain to work with, right? So what we've learned from the liver is that's not the case. Liver cells, hepatocytes, taken out of the body and put on a petri dish surface last 48 hours. We've now shown that they can last 40 days or longer if you put them in the right 3D environment, which is surrounding them with liver cells and the other cell types that they like and keeping them in the best way possible. So, you know, philosophically or just in an abstract sense, we have to be able to achieve it, but we have to be able to direct that environment exactly correctly. And we can't quite do that yet, but we're getting there.
Xiaoqian, do you think that we're going to get better and better at encouraging these cells to do what we hope they'll do naturally?
Sure. Yeah. You know, in terms of your question, cells do communicate with each other, either in the petri dish or in the engineered tissue. And they like to have all these cues, we call mechanical cues, the architecture, because cells, they have lots of sensors, nanoscale. They see the environment, they talk to each other. So they know when to stop growing. They know when to stop migration. So that's why the bone cell give you bone structures, and they stop at the right size. They don't go actual miles outside your body.
Anybody speculate that cancer is a failure to communicate? See where I'm going? We didn't even have to go there. Let's go back out here. I know, we got somebody in the back, and then we'll get up to you in the front here because you've had your hand up for a while. Hi.
Yeah, hi. So we've seen for a while now, like ears growing on the back of rats and people's noses growing on their foreheads and things like that. Is 3D bioprinting currently involved in any of that process? And if not, how is it going to like accent or improve or even replace what we're doing right now with that sort of thing?
Keith?
So you're referring to, I think in the mid-90s there was an ear structure, the tissue engineered ear structure that was almost being incubated on an animal, essentially by being placed under the skin of the back, the dorsal skin. So I think that's what you're referring to, and I haven't seen that from 3D bioprinting yet specifically, but you know, I think it is interesting to contemplate the body as an incubator. So one of the things that has been done, I think it was a group in Belgium that worked with a human trachea that they were trying to grow, and one of the challenges was allowing the patient's own cells to grow on that. So they actually, after they fabricated it, they didn't use 3D printing, they used a different method. They put it in the patient's arm for a while to get it vascularized and let it grow, and then implanted it so that it had a blood vessel system and it was more ready to be used in the actual windpipe and replace the windpipe that was there. So I think that whole concept of incubation in the body gets back to what I was saying. If you surround it with the right environment, it can only perform the right way.
Andrew, have you heard of this kind of thing?
I have, and I've tracked some of the stories. I think what we're really dealing with here is we have a long way to go before we can perfect the incredible microenvironments that our bodies generate. Remember, our bodies are based on really 4 billion years of design engineering, but we're catching up quickly. And we have millions of people that will come into this space and we can learn from. So it'll happen faster than most people think. So that's important to remember.
We'll try and get in a couple more questions here from the audience. Before, gentlemen, I'm going to go back to you in way of closing, let you talk about where your research, where your work, and in your case, Andrew, where maybe Autodesk is hoping to go. Right up here in the front, sir. Hi.
I would think eventually the ethicists would have a hard time with this. I mean, you can do a lot of good with it, but you can also start making sports obsolete because you can build football players of any capability you want. You can go into space travel. It wouldn't have to be an exact organism. It would be one that could withstand all the radiation, and it could just be in something entirely different than we are. And at what point do you just say we'd rather have humans because we'll just not be worth anything anymore?
And where do you cross over from human to something else? I don't know how many of you heard the short conversation I had with Nick Roman, the All Things Considered host here on KPCC earlier today. But Nick actually said, so ask these guys if they can make me a 7-foot NBA player, because he's wanted to do that for a long time. So, Andrew, is this a question that ethicists are starting to look at? You know, do we have the right to change what it means to be human?
I think we're going to bump up to that in the next century or two, whether we don't really have a choice in it. As we understand more about the manipulation of life, we have to start looking at some of the issues around it. We've been fortunate that most of the issues we've dealt with today are relatively uncomplicated. So, but I think it's just something that's just going to keep coming to the forefront. A lot of it might get solved quite naturally as the technologies move forward. I'm not too worried about the transhumanists taking over today because I don't know any.
Well, we'll talk to Ray Kurzweil about that sometime. Keith, do you have any sobering thoughts in this direction?
I mean, I'm a pragmatist, and I would just say, I mean, ethics always shakes down to good and bad, and good uses of the technology are going to be things that everyone supports. Bad uses of the technology are going to be things that everyone frowns upon. At the edge, you're going to have the gray area stuff that people spend a lot of time thinking about. But that's true of any technology. It always has been the case. I mean, you know, people had ethical problems with using cadavers for medical research, and look at how much that has helped humanity, right?
Xiao Chen?
At this stage, I worry more about, you know, where to get a grant to support my group. I think that could be an issue, but not at this moment for me. From research point of view, I'm looking at fundamental science, what we can do better in terms of, you know, making those functional tissue or organ.
We'll bring in the UCSD philosophy and theology departments at some point, I'm sure. I think let's try for one more question before we wrap up. And there are a couple up toward the front here. We'll let Janice get to someone. Hi, sir. What's your name?
Hi, I'm Ian, and this is for Keith. You mentioned that you create small pieces of tissues, human tissues, and then use them, other companies use them for testing. Is that how Organovo primarily gets its revenue? And how do you see Organovo getting its revenue in the future?
Yeah, that's right. So our revenue today is primary from collaborations with pharma and other type of companies, and so that is the primary driver of our revenue. But we're very early stage, so our revenue isn't that large right now. But we are actively using these in drug discovery research, and we'll continue to grow that. So the 3D liver, the ultimate goal for that is to actually have, you saw the multi-well plate in the animation, is to have a structure of 24 little 3D livers in one single plate that we would sell as living tissue for use in toxicology research in pharma and in other research labs. So that's another source of revenue that's downstream for us.
One of these collaborations was there was a company that helped you develop the printer, right? The bioprinter, which I have to give the name of because we haven't done it yet. It's such a great commercial name, the NovoGen MMX. That's pretty cool, isn't it?
Well, thank you. I came up with that.
You're welcome. I think, we've had someone who's been so patient down here in the front, and then we'll just do a quick wrap up. Thank you, Haley. Hi, ma'am. Just wait for the microphone there and introduce yourself.
We are two of us.
Oh, two of you.
Okay, we are friends. My name is Neda Fabris. I am a mechanical engineer professor, so I don't know enough about biology. But I wonder, what is the difference between animals who regrow their own organs? Did anybody understood how they can do that? And is this similar? Basically, I mean, they have to remember the shape of the organs to make a tail, if the tail is cut or so on. And what really makes them to remember that? Does anybody know that?
Interesting question. Amphibians, reptiles, they can regenerate whole portions of their body. I mean, does that enter into this discussion?
So there is not a lot of understanding of the mechanisms by which that work, but certainly people are studying that and trying to understand it. So salamander example, salamanders can regrow full limbs, geckos can regrow tails, things like that. So there's clearly some understanding we can have from that, but I don't think we necessarily expect that we're going to be able to reinduce that in mammals. I think you're going to have to start from an understanding of what's going on at a molecular biology level and then leverage that to accentuate what you're doing to tissue engineer a structure. But I don't think you're going to be able to start with an amputated limb and get to the full limb through the same type of processes.
Well, who knows in the future, but at least we don't see that clear pathway right now, I suppose. Gentlemen, we better wrap up. Andrew, I want to go to you first about where you hope this will go and where your own interest is going, and maybe that of Autodesk.
I really look at this as the next computing industry, the next big IT industry, and I just hope that this program and the speakers that we've had on today inspire people to explore this space and potentially connect into it with software tools and hardware tools and life science to keep it growing.
Keith, knowing that you may not be willing to share absolutely everything that Organovo has going on in the lab, where do you hope to be?
Well, I think we talked a little bit about the different ways Organovo, achieves revenue. So in the future, what we'd like to be is a partner to a large number of pharmaceutical companies who have discovered drugs using the tissues we make as a disease model. That would be the first thing. So you're looking for a lung fibrosis drug, you work in a lung disease model, a lung tissue disease model, find the best drug activity, and then you're taking that forward in clinical trials. We talked about this a little bit before. Partnering in the design of those clinical trials to make patient-specific decisions and understand how to match the patient's genetics with the performance of a drug. So use an IPS type of cell, induced pluripotent cell. From
IPS?
IPS, that's the cell I was talking about earlier. You can take a patient's skin cell, back it up, and then use that. If you can say, I want to know what percentage of the population and I want to know the genetics of the population that's going to respond to a drug, you can study, once you have a human disease model, you have the ability, very different from an animal model where you do an N of 8 and then you take the average and that's your answer. You have the ability to produce 100 or 1,000 disease models, tissues from different people, from their genome. And so then you can then study how a drug works across a population, and then you can design clinical trials in a superior way because you can screen out people that won't respond, shrink the study cost, and have a better chance of having success in that study because you've taken a bunch of zeros out of the study, essentially in terms of the numbers. So That's another thing I'd like to see happen. There's a potential to use this in diagnosis and treatment. So in cancer, for example, print from a patient's own biopsy material, a small bioprinted cancer model that's going to allow you to test different drug regimens and give that patient personalized cancer. And then, of course, cancer therapy. And then, of course, we want to have tissues in clinical trials and advancing towards becoming therapies by direct use of bioprinted tissues in surgery.
Xiaochen, you get the last word. Where are you hoping your research will take you?
So we will keep our tradition in terms of challenging the wisdom of what we can do in the future. So we will keep pushing those challenging issues, including this printing resolution issue that we are doing now. We are trying to make more functional structures from research point of view. On the other hand, we work for the university, so we want to educate more students and want to generate more bioprinting engineers, so larger scale engineer or even nano scale engineer for bioprinting. So I appreciate this opportunity to share our work with the general public, and we hope we can get more interesting from everybody here and get a message out. We do have classes at UC San Diego teaching topics like this one. So thank you very much.
And I have no doubt but that this is only going to become more interesting and more exciting. Really, our guests have made this an utterly fascinating and I find uplifting conversation. And I really do wish all of you the greatest of success in your work. And I will gladly welcome back the first of you who can build me a new brain. I'll settle for a new nose. Let me thank one more time Andrew Hessel, Keith Murphy, and Xiaochen Chen. Please join me. My thanks also go, as always, to the outstanding staff of the Crawford Family Forum. They really always make these evenings very easy and great fun. That's Technical Director over there, Dave McKeever, who's been running all the equipment for us, including our conversation with Andrew. Jenny Smith is not with us tonight, but she's the forum coordinator. Jason George is in the back there. He's been running the webcast, and we do want to thank all of you who've joined us online at scpr.org. Also helping out tonight, Haley Waters and Luis Gomez back there, I think, tweeting for us. You've been doing that, Luis? Hope you got some good stuff out there. Thanks. Forum producer, Janice Watchie-Hurst. She's the one who keeps me sounding smart up here. And then there's the practically perfect John Cohn, who already has at least 2 brains and 3 hearts. He's SCPR's managing producer of forum programs and live events. This next program will soon, maybe very soon, maybe tonight, be available on demand at scpr.org. Next returns in December for an evening devoted to the intersection of science and faith. And in the meantime, I'll be talking space exploration every week on Planetary Radio. Thank you, everyone, for joining us. Have a great night and a great future. And then there's the practically perfect John Cohn, who already has at least 2 brains and 3 hearts. He's SCPR's managing producer of forum programs.